Alright everyone, welcome back. Today we will be talking about the definition of a limit. What was that? Now, last time we saw how the average velocity and the instantaneous change were related. We also spoke a little bit about secant lines and tangent lines as well. Now, those are just two of the very important topics that we'll be discussing later in the course. So I was just mentioning that in passing as they will prove to be very important. Today, we'll be talking about the definition of a limit, or at least the preliminary definition of a limit, because there is a more deeper definition, I should say more mathematically sound definition, that we will see a little bit later on when we talk about continuity. Whatever that is as well. So every time that I introduce a term that I haven't defined, like that I speak about, I will always say whatever that is. Just keep that in mind. So let's first define what a limit is. So I'm gonna try typing most of this. I'll try typing most of it. So suppose the function f is defined for all x near a. A is a real number. X is also x are also real numbers. So near a, except possibly for a. If f of x is arbitrarily close to a, if f of x is arbitrarily to L, and we could actually make this as close to L as we like, for all x sufficiently small, then we write the following. Let me just expand this. We write the following. We write that the limit, this is how we write limit, as x approaches a of f of x equals L. So again, we say, or we read this as the limit of f of x as x approaches a equals L. Here in this definition, L, a, and x are all real numbers. F is your function. So basically what this is saying is that if you have some some number, then as you travel along that function and you get closer and closer to this value a, you will get some output value L. You get some position value of L, and that's what we call the limit. And this is true for any function that has a limit. If the limit exists, then we can find it. So again, informally, we say that the limit of f of x equals L. I'm going to write it like this because if I'm typing, I cannot write limit of x approaches a. So this is true if f of x gets closer and closer to L, as x gets closer and closer to A. Now, the value of this limit, if it exists, depends on the values of f near A. So the values of this limit, if it exists, depends on the values of f near A. However, it does not depend on the value of A. And when I say A, I mean f of A, the output value. Sometimes the limit L will be equal to the output value of the function f at A. However, this need not be always the case. So that could happen, although we are not guaranteed that it will happen every single time. All right, so let's do an example. So let me try to draw a plane here. Let me try to draw a nice function here. So I have 1, 2, 3, 4, 5, 6. And on the y, I'm going to go 1, 2, 3, 4, 5. Actually, let me just use the ruler, so it'll just look nicer. I'll take the time to do this. Alright. So I have x, I have y, and then x. Alright, so x, y. So I have 1, 2, 3, 4, 5, and 6. Not to scale. 1, 2, 3, 4, 5, and 6. Obviously, we have the negative values, but I'm not gonna write them. So we have the following function. So we have a function that kind of looks like this. At 1 is 2. At 2, it goes through 3. Goes through 3, and then 4 kind of like eases up. So this is y equals f of x. Now at 2, we're actually up at 5, and we have an open hole here, and we have an open hole here. So let me erase this. Okay, so this is our function, and it continues to go on either side. All right, so we could actually find the limit of a function by using its graph. So it turns out that we can find the limit of a function at a particular point by using the function's graph. So if you could graph the function, then you could find the limit at any point. So my first question is, Number 1, what is f of 1 and what is the limit as x approaches 1 of f of x? So I have two questions here. What is f of 1 and what is the limit as x goes to 1? So, I mean, I know my picture is not perfect, but as x goes to 1, if we plug in 1 and we go up and across, we get that this is the point 2. So we have that f of 1 equals 2. Okay, if you plug in 1 for this function, you get 2 as the output. Now, what is the limit as x goes to 1 or as x approaches 1? So limit as x goes to 1 of f of x is what? Well, to find out what the limit is, we have to look at what happens to the x values as they approach f of 1 on both sides. Okay, or as they approach x of 1, x equals 1 on both sides. So what do we have here? We have x values traveling from the right side all the way to 1, and then we have x values traveling, this is the right side, the left side, to 1 as well. So as these x values are traveling on the x-axis, remember they all are real values and they all have output values on the function above. So as you are traveling on the x, you're moving, from right to left on the function, and similarly you're going on the other side from left to right. So you begin to approach a particular value. As you get closer and closer to 1, we see that these blue arrows that I drew are getting closer and closer to 2. So we can conclude that because the x values as we approach 1 from the left and the right side both go to 2, we will conclude that the limit is actually equal to 2. So again, we have to look at the values of x as they get closer and closer to 1 on both sides of 1. So number 2, what is f of 2 and what is the limit as x approaches 2? Okay, so what is f of 2? If we go back to this line, we could see that, first of all, I didn't draw it to scale. Number 2, we have an open hole, and I did mention that the open hole was at 2, so just bear with me, just make believe that this is a straight line. So if we have an open hole at 2, that means that this point actually doesn't exist there. But we have a point up here, and that point corresponds to 5. So that means that the value of 2 for this function is actually 5, not 3. So f of 2 equals 5. Now what is the limit as x approaches 2 in this function? And I'm going to continue to use green for this one. So the red stays the same, but instead of approaching 1 now, we are approaching 2 from all the sides. So as we approach 2 on the x-axis, what's happening to our function? Well, we're getting closer and closer and closer to this point right here. And what point does that correspond to? Well, that corresponds to 3. So we can conclude that the limit as x goes to 2 is equal to 3. Okay? And that's again because we are approaching the x value of 2 from the right and the left side, and as we approach it on the x values, the output values in the function are getting closer and closer to 3. It is true, because of what we just checked, that at x equals 2, f is not equal to 3, x is equal to 5, f is equal to 5. But this goes back to what I was saying, that uh, sometimes A will be equal to the output, but other times it will not be. So this is an instance where the limit is actually not equal to the output. Okay, so let's look at one more using this example. What is f of 3? And what is the limit as x approaches 3 of f? Well, f of 3, if we go back and look at the function, and let me try to use this color. Just assume again that this is a straight line, even though clearly it's not. F of 3 has an open hole, and there's actually no other point that corresponds to it. Like for 2, we had this point up here. For 3, we don't have this. So that means that f of 3 is actually undefined. It's not part of our domain. So again, it is a vocabulary word from pre-calculus, both of them. So this is undefined. It's not part of our function domain because we have removed it. So we have that to worry about. Or do we? Well, let's look at the definition. The definition of the limit means that the limit does not depend on A. So I believe I wrote this somewhere here. Yeah, right here. So it doesn't depend on the values of the output for A. So we could actually find the limit for points that are undefined with any function that has an undefined point. It is possible to find the limits. So let's see if this will be the case for this particular function that we're working with. And let me see if I can actually change colors. It goes like purple. Right, so if we're looking at 3 now, we're getting closer and closer to 3 from the right side and from the left side. On the x-axis, what this means is that I'm making the values from the left to right bigger because I'm going 0, then 1, then 2, then 2.5, 2.7, 2.8, 2.999 from the left side. From the right side, I'm going smaller. So I'm going 6, 5, 4, 3.5, 3.2, 3.1. And what's happening is that I'm evaluating all of those points. And I'm looking at what's going on my graph. So I go climbing, 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 climbing till I get here. And I'm going from right to left on this side. And we approach this point right here. And this point corresponds to 4. So on the right side, I get closer to 4. On the left side, I'm getting closer to 4. And because we are actually getting closer to a number, we can conclude from both sides, we're getting closer to the same number. We can conclude that the limit as x approaches 3 of f of x is actually equal to 4. So it exists and it equals 4. Because again, we are approaching that value. So, another way of viewing this, you're moving closer and closer to this 4. All right. All right. So that is if we have the picture of a function. So much like we did in the previous lecture, which I still have the function of that lecture here. Let me just delete all this. If you are given the graph of a function, then you should always be able to find the limit at a particular point. So for example, if I give you the following graph, I'll just make a simple parabola. Okay. So now we have a nice parabola here. If I were to ask you to compute the limit as, let's see a nice point over here. It's like so anticlimactic. All right, so let's look, for example, at the point -1. So you're looking at this point right here, -1. For -1, as we approach -1 from the left, you could see that in the function we are beginning to move down. So for -3 we have a big value. For -2 we have 1. For 0 we have whatever point this is over here. For -1.5 we have -1. So the values from the left side are all getting smaller. We went from 1, 0 to now -1, -1.5 eventually, and finally -2. And from the right side, the same thing is happening. So as we move on from the right side, closer and closer to -1 on the right side, the function values are also getting smaller. So remember, the function values, you plug in x, and then you get the y. So as I get closer to -1, I'm plugging in 1, and that gives me an output all the way up there. Then I move to 0.5. Now the output is just 1, so it got smaller. As I keep moving closer to this -1, I'm getting closer to some number down here. So I go to 0, I get -1 as an output now. So now I became even smaller. I go to -0.5, and for -0.5, you're already like almost at -2. Actually, you are at -2 at -0.5. For -0.9999, you are basically here. I mean, we could even zoom in more so you could see what I mean. So -0.8, you're here. So you're getting very close to this point right here. So as we approach -1 from the left side and the right side on the x-axis, our output values are getting closer and closer to -2. So that is why we say that the limit here is actually 2. Now, what if I made this an open hole? So let me just draw this white. So we have an open hole. And now let me just put another point here. So let's say now that this point is just 1. So now we have a whole different situation. The output value for the function is no longer -2, it's now 1. However, the limit is not changed. Why? Because as you move closer and closer to -1, the output values of the function, both from the left and the right side, are still moving towards -2, not to 1. So this is a quick illustration, or a better looking illustration of what I was just saying. Now, finding limits visually with the use of graphs is useful, but it is not always possible. The reason why it's not always possible is because, sometimes you're not given the function, the actual function to graph. So if you're given, you're given the function, it's going to be very difficult for you to actually plot it. Some functions are just difficult to draw, and you will have to draw a lot of points to actually make sense of what the limit will be. So we could actually use a table to find limits. So we can also use a table of values to compute limits. And this is very similar to what we did in lecture number 2 with the rock example. So let's see, let's do an example. Let's find the limit as x approaches 1 of the following function. So the function is f of x equals the square root of x minus 1 divided by x minus 1. So this is already a complicated function. We have a radical in the numerator, we have a rational function as a whole, and we have to find the limit as this approaches 1. So since we find the limit, we do limit as x approaches 1. So what we're going to do for this table is we're going to have our x values and we're going to have our output values. Remember, x is the independent variable, so we get to pick whatever values we want for it. So let me use a ruler. So what do we have here? And let me actually flip it as well. Yeah, this is fine. All right, so I'm going to pick a bunch of numbers between, well, that are very close to 1. Since I'm looking for the limit as x approaches 1, so I'm going to look for numbers to the left side and right side of 1. For a lot of these problems, you might want to use a calculator. With this estimation, it's okay to use a calculator because doing this by hand could be very messy. So let's see. The first number that I'm going to use will be, let me see, 0.9. Let's use that. And the second one is going to be 0.99, and 0.999, and 0.9999. So you can see I'm getting very, very close to 1. And from the right side, meaning numbers bigger than 1, I'm going to do 1.001. Miss 1 0 here. 01, 1.001, 1.01, and then 1.1. So now remember that my function is this right here. So again, I'm just going to use GeoGebra to illustrate this because it's much faster. So let me write the function out. So that will be, I actually never tried to do it this way, so I'm going to try to do it this way. So let's see, f of x, I have to delete these. So let's delete these first. Okay, g of x, fine. So g of x equals the square root of x minus 1. And this whole thing is being divided by x minus 1. So this is what g is. We actually have a nice picture of it, a nice image of it, because I'm using GeoGebra. Oops. Did not want to do that. So this is how our graph looks like. Okay, so we could actually find out what the limit is eventually by doing this. So let's see. So g of 0.9 is 0.51. I wonder if GeoGebra could give it to me with a better output. Anyway, we get 0.51. Now for g of 0.99, we get 0.5. And now there are more digits. It's just that GeoGebra. Oops. There are more digits. It's just that GeoGebra is not showing me all of them. It's only displaying. It's only displaying the tens place. I gotta look into the view to actually change that setting. So I'll do it later. In any case, so let's continue on. So g of 0.999. It's going to be again 0.5. And again, it's not really 0.5. There's a bunch of other digits that are being left out. but it's very close to 0.5, so GeoGebra is just estimating it to be 0.5. So you could guess the next one is also going to be 0.5. Now, if I do the other side, 1.001, I'm also going to get 0.5. And if I do 001, I get 0.5 as well. And if I do 0.1, I get 0.5 as well. And if I do 1.1, I'm going to get 0.49. So for this ones are all 0.5s, and then this is 0.49. So as you can see, the limit of this should be 0.5. Now, keep in mind, there's a reason why I'm not doing 1. This function is not defined for 1. If you plug in 1 here, the denominator is going to be equal to 0. So this is undefined. Cannot divide by 0. This is actually undefined at, at 1. But we do have a limit. The limit, as we approach 1 from the left side and from the right side, we get 0.5. So we could say with certainty that the limit as x goes to 1 of f of x equals radical x minus 1 over x minus 1 equals 1. This is abuse of notation here. I either should use f of x or the function. So I'll just use the function because I'm really abusing notation right here. So limit as x goes to 1 of this is 1. Okay, so this is how you use a table to find the limit. You could use this for any function. So if I give you a function like this, like f of x equals, 2x plus 1 over 3x, and I told you find limit as x goes to 5. And again, I'm going to say goes to or approaches when I'm talking about limits. Then all you have to do is make a table of values and see what number it approaches. So let's see what happens here. And I'll just do this one really quickly. So I'll just pick two numbers because I'm just trying to illustrate the example, 4 and 6. 4 and 6 are actually still very far from 5, but this will give you an idea. If you plug in 4, you got 2 times 4 plus 1. That should be 9 divided by 12. So you get 9 over 12. And the other one you get 2 times 6 is 12. So this is 13 over 18. So you could continue to do this for smaller values like 5.5 and a bigger value like 4.5. And you will see that they will eventually begin to approach a particular number. For this problem, that number is going to be 11 over 15. Once you do it, you'll see that this will be the case. Okay? So now, this is all nice that we could actually create this type of tables to find limits. Now, sometimes what happens is that the limit only exists for one side and not the other. So sometimes you may have something like a piecewise function where the limit from the right side is completely different than the limit from the left side. And these are called one-sided limits. So these are called one-sided limits. Okay. So first of all, the limit, and it's going to be so. I'm going to try to figure out a nice way of doing it. But for now, what I'll say is this. When I type in LM, I'll do LM f of x. And this will be for limit as x goes to a of f of x when I type it. That's a nice conversion. So the limit LM f of x equals L is referred as a two-sided limit because f of x approaches L approaches L as X approaches A for values less than A, and this is important, N for values bigger than A. X values bigger than A. Now, for some functions, as I was mentioning, it will make sense to examine one-sided limits, which are called left-sided and right-sided limits. So yeah, the piecewise defined function is definitely one of these functions that we will use one-sided limits with. Another function that we may use one-sided limits will be something like the absolute value function. It is definitely useful to, I mean, you'll see that it will be the only way that we'll probably be able to find limits for that. All right. So let me give you a definition for this too. So definition. So first of all, let's start with right-sided limits. Okay, so suppose f is defined for all x near a with x being positive, meaning x being greater than a, not necessarily positive, but x being greater than a. If f of x is arbitrarily close to L, for all x's sufficiently close to A with x being bigger than A, we write the following. And that is the limit as x goes to A from the right side with a plus here of f of x equals L. And we say, so we read this as the limit of f of x as x approaches A from the right side is L. As x approaches A from the right side is L. All right, so let me actually rewrite this because this looks ugly. Okay, so we say limit as x goes to A from the right side of f of x equals L. Okay, so we use a plus sign on top of the A. Whenever you see this plus sign on top of the number, that means that you're evaluating the right side limit. So just as a quick example, this will look like limit x as x goes to 3 from the right side of, let's say, 3x plus 2. Okay, so that's one way that you will see this, or the way that you will see this in this class, at least with me. All right, what about left-sided limits? Well, for left-sided limits, we have the following. Suppose that f is defined for all x near A with x being less than A. If f of x is arbitrarily close to L, close to L for all x sufficiently close to A, with x being less than A, then we write the following. We write that the limit as x approaches A from the left side of f of x equals L. So instead of writing a plus sign now for the left side, we write a negative sign. And this makes sense. If you think about the real number line, positive values are to the right of the origin and negative values are to the left of the origin. So this is a nice way of remembering that a to a minus sign, when we're talking about limits, means left side, and with a plus sign means the right side. So we say that the limit of f of x as x approaches A from the left side is L. So this is how this is pronounced, this symbol. Now, let's just unpack this whole thing. So we have that f is defined for all x near A with x less than A. So this makes a lot of sense, because if you have, if you look at the number line, let's say this is A, then we're talking about x values that are less than A. So no, this means that you're to the left side, as opposed to here, where we had A values and we're looking at x values that are bigger than A. So here x is bigger than A. Here x is less than A. So this makes a lot of sense here. So if this is the case, then we write the left and right sides limits as we did. Okay? So let's talk about an example for this. Let's use either tables or graphs to actually solve the following right side and left sided limits. So, example, let f be given, f of x be given as below, and compute the left and right sided limits as x goes to, I will say approaches this time, approaches 2. And this is the function. So f of x is defined to be x cubed minus 8 divided by 4 times x minus 2. So let me just quickly plot that so you could have an idea of what we're dealing with here. Let me close this. Let me actually remove this as well. So we have, and I'm going to call this h, just already used the other ones. So I have x cubed minus 8 divided by 4 times x plus 2, no, minus 2. Okay, so we have our function here. So this is how it looks like. Okay. And we are interested in finding out what's going on when x equals 2. So we could see from the graph that we seem to be approaching 3. You know, visually we see that as the values get closer to 2 from the left side, on the function we are getting closer and closer to 3, and as we approach 2 from the right side, we're getting closer and closer to 3. But we will still look at, you know, what the limit actually are from the left and right side. The reason why we're going to do this, and we're not going to focus on the graph, is for the following reason. Notice that f of 2 is equal to 2 cubed minus 8 divided by 4 times 2 minus 2. What we have here is that 2 minus 2 is going to be 0. So we're going to have 2 cubed minus 8 divided by 4 times 0. And this is actually going to be undefined. And it's not going to be undefined, this is actually called indeterminate form. And we get indeterminate form when we get something like 0 over 0. We call this indeterminate. For the purpose of this class, we could also call it undefined. But if you want to really be proper, we're going to call it this indeterminate. Okay, so we're going to have the fact that for 2, we're actually not defining this function, so our graph is misleading. The graph that we have here from the algebra is actually misleading. It's not really correct. So we have to be even more careful now when computing the limit. So what I always suggest to do is make a table of values. So we are interested in finding out what the function f is as we approach 2. So much like we did it with the previous problem, with the radical, we are going to make a table of values. So we could estimate what the limit is. Remember, we are interested in finding out what the limit is as we approach 2. Alright. Okay, so if I'm interested in finding out the values as x approaches 2, then I'm going to begin with values, that are somewhat close to 2, like 1.9, 1.99. As if you haven't picked up the pattern right now, we're beginning with tens, hundreds, thousands, and just moving closer and closer to that value of 2. Once you get to the 10,000s, you should be okay. It should be far enough for you to actually tell whether the limit exists or not and what it is. Okay, so again, I'm gonna simply just use GeoGebra if you're home and you have a problem like this. It is okay to use a calculator because at this level, I trust that you know enough pre-calculus to be able to understand that we're simply just plugging in these x values into our function and getting an output. So this is why we could get away with simply using technology for our advantage. So let's define our function. Let's actually define, we already have it here. I have it defined as h. So 1.9, we get 2.85. And actually, I'm not even going to use GeoGebra because I'm going to take this time to actually show you a nice website called Wolfram Alpha. Wolfram Alpha is a pretty powerful calculator that you can use to do this type of computation. So let me just type in our equation. So we have this. So here's what we have. So we have x minus 2 here. We have x cubed here minus 8. So I'm just going to be changing, obviously, the values for x. So this is going to be 1.9. And here is, actually, I don't even have to do that. I could just say for 1.9. So I could just say evaluate this for 1.9. And Wolfram will give me the solution. And make sure you put parentheses correctly, because I just didn't. It's not there. So we have 2.8525, which is what I wanted to get. So 2.8525. If we now do 1.99, we have 2.98502. So 2.98502. If I do 2.999, or 1.999, we have 2.9985. So 2.9985. So as you can see, much like we saw in the picture on GeoGebra, we're getting very close to 3. So let's just do, did I actually write this like twice? I just realized I wrote this twice. So 1.999, so 1 extra 9, the fourth 9, it's going to be 2.9999985. So 2.99985, and these are the same, so just erase it. That's an oversight on my end. And now 2.001. And we're going to get 3.0015. So 3.00015. We remove 1 0, we get 3.0015. If you remove another 0 here, you're going to get 3.0015 02, and finally 3.1525. So as we can see, the closer we're getting to 2, remember 2 was undefined, the closer we're getting to 3. So what can we say about this? Well, we now have that we actually just found both the left side and the right side limit. So we can see that the limit as x goes to 2 from the right side of f of x is 3. Because the closer we get to 2 from the right side, the closer we're getting to 3. And similarly, from the other side, the closer we get to 2 from the left side, the closer we're getting to 3. So we have that the limit is actually 3. So let me write this down, because, or since, why did it go all the way up there? All right, so we have since the limit from the left side as we approach 2 is 3, and the limit from the right side as we approach 2 is also 3, then we can say with certainty that the limit as x approaches 2 for the function is 3. So because the limit from the left side and the right side are equal, we can actually say that the limit overall, the two-sided limit, is actually 3. So you could actually simply say limit as x goes to 2 of f of x is 3. So this is certainly a more nicer argument to make. Now, based on this, you may wonder whether the limit from the left side and right side always exists, and are they always equal? And that is not necessarily true. So you may have right side or left side limits where you may have limits where one of them exists and not the other. You may have limits where neither one exists. You may have limits where both of them exist, but they're not equal to each other. So I'm going to write a theorem down, and then I'm going to go over one more example which will illustrate this. Okay? Actually, 2 more examples, and then it should be done. So this is a theorem which I will not prove, at least not yet. And it basically tells you the relationship between one-sided limit and two-sided limits. Okay, so let me actually remove this right there. So, theorem says the following. Assume f is defined for all x, defined for all x near a, near a, except possibly a, then the limit as x goes to a of f of x equals L if and only if and only if the limit from the right side as x goes to a of f of x equals L, and the limit from the left side as x goes to a of f of x is also equal to L. In other words, this is saying is that this limit, it's the two-sided limit, is only true if, and I will say this again, if and only if the right side equals the left-sided limit. So an if and only if statement means that both sides of these things have to be true, meaning that if the left side limit is equal to L, then the right side limit must also equal to L for this two-sided limit to be equal to L or to exist. Again, I will not prove this theorem, at least not in this class, but I could definitely go over the proof with you during office hours if you're interested in seeing it. Maybe I should have typed this because it's a little bit difficult to see. All right, so let's see an example of this. Let's say we're working with the following function. Let's say we're given g of x equals 2x squared minus 6x plus 4 divided by the absolute value of x minus 1. Please don't crash on me. And it did. Alright, let me just open this back up. That had not happened in this video. Alright, so let's go back at it. Okay, so we have the following function. Now, recall from pre-calculus, this is something you should definitely know from pre-calc, but if you don't know it, it's okay. That's why I'm here to remind you. F of x equals the absolute value of x means the following. It means that this is, let me not use f of x because I'm going to use the notation here. I'll do y equals absolute value of x. This means the following. The absolute value of x equals x if x is greater than 0, and the absolute value of x is equal to minus x if x is less than 0. And you could say greater than or equal for this one. But this is something that we're going to use now, and this is a fact from pre-calculus. Okay, so what can we do here? I could actually split up this g function into two pieces. Okay, so I have a piece for which, and I'm finding, by the way, I'm finding the limit as x goes to 1 of g of x. So this is what I'm trying to look for. So I want to find the limit from the left side and the right side for this at as x goes to 1. So what I'm going to do here is I'm going to write two functions. I'm going to have one for when x is bigger than 1, and I'm going to have one for when x is less than 1. So for when x is bigger than 1, what we have is the following. We have that g of x equals 2x squared minus 6x plus 4 over x minus 1. But based on this rule, because x is positive, it's bigger than or equal to 1, then the absolute value of x is simply x, meaning it's simply going to be the thing on the inside. So what this is going to be equal to is going to be 2x squared minus 6x plus 4 divided by simply x minus 1. And if you notice, we can actually factor the numerator. Everything in the numerator is a factor of it's a multiple of 2, so we can factor a 2 out. So we get x squared minus 3x plus 2 at the top, and x minus 1 still in the denominator. And if you look further, we could actually simplify this a little bit more. The inside factors a little bit more, because 2 times 1, negative 2 times negative 1 is plus 2, but they add up to minus 3. So you could do x minus 2, x minus 1, and then x minus 1 here. So as you can see, there will be some cancellation. So long as x minus 1 and it's not equal to 0, we can cancel. So we have 2 times x minus 2 left over, which is equal to 2x minus 4. So now we have one rule that when, and this is a very easy function to plot, when x is positive, we are using 2x minus 4. And then when x is negative, we're going to use the other rule. So this is when x was positive that we do in this. So now what happens for when x is less than 1? Or when x is negative? So when x is less than 1, we have the following. We have the g of x, which was equal to 2x squared minus 6x plus 4 over absolute value of x minus 1. Based on our rule of absolute values, that denominator, the inside, is going to become minus x. So what I'm going to have here is that g of x equals 2x squared minus 6x plus 4. The numerator stays the same, but the denominator, instead of writing x minus 1, I'm going to write minus x. But the x is x minus 1, so it's going to be minus x minus 1 with a negative on the inside. We already know what the top factor, so I'm just going to factor it right away. So this was x minus 2, x minus 1. Now notice that I have x times have minus x minus 1 here. Okay. So we could actually cancel out again x minus 1 and x minus 1, and I have a negative sign, a positive sign, and a positive sign, so this is just negative 2 times x minus 2, so I get negative 2x plus 4. So now I'm working with two functions, with two graphs. So basically what I'm doing here is that I was able to simplify my function g, and instead of using this definition of the function, or rather this definition of the function up here, what I've done is I've created a piecewise defined function, and this piecewise defined function is equal to 2x minus 4 if x is bigger than or equal to 1, and negative 2x plus 4 if x is less than 1. So that's what we've done so far. So let's try to plot this. These are two linear equations or linear expressions that we have here. So they're pretty easy to graph. So for when x equals 1, I'll use the top function. So that's 2 times 1 minus 4 for the top. So 2 times 1 is 2. 2 minus 4 is negative 2. Last time I checked. So we have a point down here, 1, negative 2. And then if I go, remember for a line we only need 2 points. So I'll go up to 2. So 2 times 2, and I'm still using the first graph, the first equation, because I'm still dealing with numbers bigger than or equal to 1. So 2 times 2 is 4. 4 minus 4 is 0, so I get a point here. So this looks like this from left to right. For the other one, I'm strictly less than 1, but I still want to find out what happens at 1. So I'm still going to plug in 1 there. Just keep in mind we're going to have an open hole. So 2 times minus 1 is minus 2, and 4 minus 2 is 2. So we have, if we were using 1 as part of the domain, we will have a point here, but because it's not, we have an open hole. Now a number less than 1, certainly 0 is less than 1. Negative 2 times 0 is 0, plus 4 is 4, so we get the y-intercept at 4 up here. So we have a line going down from left to right. Okay, so now we could actually figure out what the left-sided limit is and the right-sided limit is as we approach 1. And yeah, and we could see the following. So if we look at the function and we look at the right-sided limit first, let's say as x goes to 1 from the right side of f of x, what do we have? Well, as we approach 1 from the right side, meaning as we go in this direction, what's happening to our y values? Well, our y values are going down, and they are approaching negative 2. So the limit from the right side is negative 2. However, the limit from the left side, as we approach 1 from the left side of f of x, values are coming from this side now towards the 1. So that means that in our function, the values are coming down, the outputs are coming down, and they're approaching a particular number. This number that they're approaching is positive 2. So these two limits are not equal. So notice the right-sided limit and the left-sided limit are not equal. So this is pretty big. It's a pretty big observation that we have. So what does this mean? Well, by the theorem that I just wrote above, so let me type it. I can't even think of which one. So by the theorem from before, from above, since the left-sided limit and the right-sided limit are not equal, then the limit, and I said f, but this is supposed to be g, not f. This is g of x. So by the theorem from above, since the left-sided limit and the right-sided limit are not equal, then the limit as x approaches 1 of g of x does not exist. Why? Because the limits were not equal. So since limit as x goes to 1 from the left side of g of x is not equal to the limit as we approach 1 from the right side of g of x. For a limit to exist, for the two-sided limit to exist, both the left side and the right-hand side limits must be equal. Okay? So, last thing that I will mention is the following interesting example. I'm not going to go through it today, but we will certainly touch on this in the future. So let's take a look at the graph of cosine of 1 over x as x approaches 0. So what does this mean? I'm going to be taking the limit as x goes to 0 of cosine of 1 over x. So let's recall what the graph of cosine looks like. Let's say, so we have cosine of 1 over x. And it's this beautiful, beautiful thing right here. So as we approach 0 from the right side, what's happening? Well, first, if you begin at 2, you notice that the values go down. And they go down all the way to -1. Then they go back up to 1 very quickly. Then they go back down to -1, and then back up to 1, and back down and back up. To the point that it doesn't even look like there are lines here. It just looks like this is drawn in. If we zoom in, the more we zoom in, the more we will see the lines. But as you can see, things are moving very quickly here. Now, if you were to simply focus, if we were to make a table, for example, and we were just to focus on the values like from, I don't know, let's say 0.6, 0.4, even down here in these values that are very close, you may be tempted to say that the limit as we approach 0 would have been -1 or even 1, depending on which side you began looking at first. This is not the case with this particular graph, because notice that the closer I get, I cannot even distinguish what's going on in here. This particular function has an undefined, not undefined, it has, the limit does not exist as you approach 0, because it moves very quickly between 1 and -1. The limit from the right and left side just move very quickly between 1 and -1. So there's going to be something very important that we will see moving on in the rest of the semester. This oscillation with this particular cosine function. There are other functions that react in this way, other functions dealing with trigonometric functions. We will see those as we move on in the semester. Thank you for your attention.